All right, so in this video, we're going to prove that the derivative of the natural log of x is equal to 1 over x. And we're going to prove this under the assumption that e is equal to the limit as k approaches 0 of 1 plus k to the power of 1 over k. So, how do we actually start this proof? Well, let's start out with the definition of a derivative, expressed as a limit. Right, so this is the definition of a derivative as a limit, and we're going to replace our function with natural log of x. So we essentially have to show that this limit is equal to 1 over x. So then, where do we even start? Well, we sort of just have to play around with it. Notice that we are subtracting two logarithms. Well, if you recall, whenever you're subtracting logarithms, you can combine it into a single logarithm. And this is the property that justifies that. So we're going to apply this property to what we have in the numerator. So this is what our limit becomes. Now, dividing by h is the same thing as multiplying by 1 over h. So this is our limit now. And notice we have x plus h over x. Well, we can re-express this as x over x plus h over x, which is really just 1 plus h over x. So this is our limit. So then what we're going to do at this point may seem a little weird, but we're going to call h over x a new variable m. So m is equal to h over x. Therefore, h is equal to mx. But we're going to say that this equation is strictly a relationship between m and h, right? M and h don't depend on x. And therefore, as h approaches 0, m approaches 0. And as m approaches 0, h approaches 0. So we'll say that this is true. So then why can we say that m and h don't depend on x? Where is that coming from? Well, if you recall, in the definition of a derivative, as h approaches 0, right, as h becomes really close to 0, well, this limit doesn't care about x, doesn't care what x is, and therefore that's why we're allowed to say that h and m are independent of x. So remember that. We're going to use that. So let's move back up to the top. What we're going to do is we're going to replace the h with mx and the h over x with m. So this is our limit, but remember, this was the limit as h approaches 0. However, we have replaced our h's with m's. And we know as h approaches 0, m approaches 0, so we're going to write this now as m approaches 0. But since m is independent of x, that means we're allowed to pull the x outside of the limit. So this is the limit that we have to evaluate now. Now, the next thing that we're going to do is we are going to move the 1 over m as an exponent inside the logarithm. If you recall, that's the logarithm power rule. And this is the property that justifies that. So we're going to apply this property to this thing right here. So now that we've done this, now what we're going to do is we're going to apply this property of limits. I'm going to write it out just so it's super clear what I'm about to do. It's a property of limits involving composite functions. Notice we can move the limit inside of the function f. And we can think of this function f as our natural log. We're going to move our limit inside the natural log. So that's the next thing we're going to do. And so this is what happens when we do that. All we have to do now is evaluate this limit. But this limit is exactly what this limit is up here. It's just instead of k, we have m. So it's the same thing. We know that this limit is equal to e. So we have 1 over x times the natural log of e, but the natural log of e is just 1. And therefore, the answer is 1 over x. And so that's pretty much the whole idea. We have shown that the derivative of the natural log of x is 1 over x. And so yeah, that's pretty much the whole idea of where that comes from. Again, under the assumption that e is in fact equal to this limit. Right, and so yeah, this is pretty much it for this video.